Can you hear? Online?
We're online now.
Oh,
I think we are online, yes.
they can hear us?
So, okay,
Oh, yeah.
we start?
Yeah. Oh, we can start then.
Okay, we are going to start. Thank you very much, everyone. It's my pleasure to introduce today Gagandeep Singh. He is a postdoc at the Safari Research Group. He joined last year after having completed his PhD at the Technical University of Eindhoven and IBM Research. And he's doing great research work on FPGAs, on RL systems, and it's really nice to collaborate with him always. Whenever you're ready, please feel free to start.
Thank you, Juan. Good afternoon, everyone. Today I'll present our work, Sibyl, which is an adaptive and extensible data placement in hybrid storage system using online reinforcement learning. This work was published this year in ISCA 2022. First, I'll start with an executive summary. So hybrid storage systems use multiple different storage devices to provide high and scalable capacity at high performance. However, there are two key problems with the current data placement policies. First is the lack of adaptivity to workload changes, both in terms of different workloads and also like in terms of different devices. And also there is lack of extensibility to more devices. So the goal of this work was to come up with a new data placement technique that provides both adaptivity to whenever we change a workload, if we come up with a new configuration, and also to provide easy extensibility when we have like more devices than what we had before. So our contribution is Sibyl, which is the first reinforcement learning based data placement technique in hybrid storage system that provides both adaptivity and easy extensibility. And also it's really easy to design and implement. And we extensively evaluate Sibyl on real system using a wide range of workloads and show like Sibyl improves the performance by 21.6% on a dual hybrid system and 48.2% on a tri-hybrid system. And Sibyl is able to achieve 80% of the performance of an Oracle policy with an overhead of only 124.4 kilobytes. And we open source everything on a GitHub repository. So this is the outline of my talk today. So first I'll start with discussing the shortcomings of prior data placement techniques. So let's look at a typical hybrid storage system. So this one is an example dual hybrid system where we have a fast device. Where we have a fast device, which is small because it's quite expensive. And then we have a slow device, which is cheaper, so we can have more of it. And then there's an application which is divided into an address space, and each address space has like several pages. And then we have a storage management layer, which orchestrates the data movement around different devices, for example, read-write requests. And also it manages the data movement between different hybrid storage devices. For example, if you don't have enough space in the fast device, then you evict your data to the slower device. And in case you have like some pages which are performance critical, you would like them to be accessed from the faster device instead of slower device. So you promote the page from the slower device to fast device. So the storage management layer is really critical, and it has to manage and it has to take advantage of the characteristic of fast device to provide high performance. Therefore, the performance of a hybrid storage system highly depends on the ability of the storage management layer to move data and how it orchestrates all the data movement. There have been a lot of different data placement techniques in literature. However, we observe two key shortcomings that significantly limit their performance. First is the lack of adaptivity to both workload changes and changes in device characteristics. And second is also the lack of extensibility to more devices. So let's look at each of these issues. So first, I'll talk about lack of adaptivity to workload changes. So the past techniques, they only consider a few workload characteristics, for example, the size of the request or the type of the request, and then they statically tune all these parameters during design time, and they assume that they're going to work for all different workloads, which is not really true. So for example, over here, we have a CDE policy, which is a heuristic policy. And on the x-axis, we have a couple of workloads. And on the y-axis, we have the latency. So the lower, the better. And then we have RNN HSS policy, which is a machine learning based policy. And then we compare these policies to an oracle, which is the ideal case, which we would like to achieve, but it's not possible, but because it's not practical, because we are trying to have future knowledge of input access pattern, which we don't really have. So when we do a comparison, so the lower the latency, the better. We see in some cases, these policies perform better compared to Oracle, but in many of those cases, they don't really perform as good as we would like them to be. And on average, the difference could be up to like 41%, which is quite a lot. And the reason is because these hybrid data placement techniques, they consider only a limited number of workload characteristics and not all the different characteristics, which leads to this lower performance gap. And also these techniques, they lack adaptivity to device types. So because they do not really consider the underlying device characteristics. And for example, there could be asymmetry in read-write latency, or it could be there's an effect of garbage collection. So these policies are designed for like certain devices. And if we change the devices, these policies might not work really well. So for example, I have the same plot, which I showed before. And over here, we annotate with another policy, which is slow and only policy. There's nothing special about it. It's just like there's nothing intelligent. We place everything in the slow device instead of doing any sort of intelligent data movement. We observe for this kind of configuration, for certain workloads, even the slow only policy is better than having like any sort of data placement technique, because these policies which were designed, they are not really designed for this configuration. However, if we go for any other a different configuration for which these policies were designed, then we observe these data placement techniques are better than slow only. Why is that? Because these policies were just designed for this configuration and not for the other one. But in real setting, it might not be the case. We will have different settings, we will have different scenarios, and we would have to cater to those as well. So these policies are not really good for all the different scenarios because they don't really take into account the different devices and configurations. And then we'll talk about the lack of extensibility. So these policies are rigid techniques which require significant effort to accommodate more than 2 devices, because usually they are designed for like only 2, like a dual hybrid system, or at most 3. So what happens in case if you change the storage configuration, if you add like more devices, then you would have to redesign all the devices again. For example, over here, we have a dual hybrid system. You manually like wrote down the code for everything, like all the promotion cases and all the, whenever you have to demote the data from one device to another. But in case you have a 3rd device, then again, you have to rewrite the data. You will have to set the threshold again, like when the data should be in the mid device, when it should be in the slow device, and when it should be in the fast device. So these cases like require like design effort, like you spend a lot of resources doing that, which is not really good because in the end, you're wasting a lot of human resource on that. So our goal in this work was to design a data placement mechanism that can provide both. First, the adaptivity by continuously learning and adapting to workload changes and underlying device characteristics, and also to easy extensibility to incorporate a wide range of hybrid storage configurations. So to this end, we propose Sibyl. Sibyl formulates data placement in hybrid storage system as a reinforcement learning problem. So let's go into the formulation of data placement as a reinforcement learning problem. And guys, you can stop me anywhere in between if you have any issues. So let's look at the basics of reinforcement learning. In reinforcement learning, we have 2 important components. First is the agent, and the other is the environment. And the agent observes the state of the environment at every time step. And based on the state, the agent performs an action. And this action is kind of it takes into account the observation of the states, what's happening, and then the environment provides a reward. So reward is kind of a feedback which the environment is providing to the agent on how good or bad the action was. And based on this reward, the agent would try to change its policy or come up with a different action next time. So in the end, the agent's goal is to find a policy where the agent's action in a given state would lead to the maximum reward. So that's what the agent is trying to do. So in the end, your reward becomes your objective. So whatever you want to achieve, you kind of encapsulate in the reward. So let's look into the formulation of data placement as an RL problem. So over here, if we try to formulate as a RL problem, then the agent would be Sibyl. So Sibyl is our data placement agent. The environment would be the hybrid storage system. And for every time step, or you can think about it, every request, we would provide some sort of features of the current system or the current request to the agent, which is Sibyl. And then based on these features, like Sibyl would try to come up with like some action which is most optimum according to Sibyl's policy, and which would be like select the storage device where the current page should be stored at the moment. And then we provide the feedback. So in our case, we provided feedback in terms of request latency of the previous request. So because our objective in this work was to demonstrate how you can optimize for latency, but there could be any other objective, whichever you want to optimize for. And like first, if I before I go into like more into the RL formulation, I would like to briefly explain like different RL approaches. So there are like many different approaches, but if we look into like the traditional approach and the modern approach which we are using in this one, so you would have seen like many works which are traditionally using like a tabular approach. So what happens in that approach is you have a state, and then you have a couple of actions, and then you build up a table of all the state action pairs. And then each of these and then you assign a value to it, which is called the Q value, which is the kind of, you can think about it as a quality value, given a state and an action, how much is the value for that? And in the end, you store everything in a lookup table, and your goal would be to come up with the best state action value, which gives you the highest Q value. So for example, this is the value we select, and then that's the action which the agent takes. But if you think about this approach, it has been applied like in previous, traditionally, but if we go for like real scenarios, for example, even data placement, there could be thousands or millions of pages. And if you start doing the same, like keeping a table for all the different options, it would explode. There would be like a really high computation overhead, storage overheads. So that's why in this work, we went with a deep reinforcement learning approach, where in the same way, like instead of when you have a state, instead of having a table, you use like some sort of a neural network, which acts as a function approximator. So it approximates this lookup table, which you're looking at it in a tabular approach. And in the end, then it provides you with some sort of like probability or some sort of notion of what would be the Q value given a state and an action. And then based on this value, you select the action. So in the end, like this approach kind of approximates a table, and it's really way faster than having like lookups on the table. So that's why like it's quite popular. You would have seen like a lot of like works like in terms of like AlphaGo or other RL approaches which are commonly being used right now. Okay, and now I will go into the formal. Sorry,
I would like to ask you one question with respect to this slide.
Yeah.
Because now you're using, instead of using the tabular approach, you're using a neural network.
Right.
And this neural network needs to be trained, and it will have to be updated over time.
Right.
And indeed, I think that's what happens. So how is it different? Is this different from the neural network approach that was done by the RNN? Another work that you used previously for motivation. Right.
Yeah, so there was that work, like first of all, I would like to mention that work was not really for hybrid storage, it was for hybrid main memory. So we kind of, we wanted to have like some state-of-the-art machine learning algorithms. So we optimized it for our own scenario. So but still, like if you think about it, that RNN, like first of all, we know it's like really compute intensive. The overhead of having an RNN is quite huge. But the concern you mentioned about like having like computation overhead when you're trying to perform a data placement or something, we would have it as well. And that's what we tried to do. Like I'll show you like how we overcome this kind of issues, that we, instead of putting this neural network in the critical part of the decision making, we keep another separate network which is being trained in the background. So and this network is just doing the inference, and we keep updating the network in the background, and these two networks are working asynchronously. So we are able to overcome this issue of like this model being trained, and then you are doing the data placement, and instead, because we have two separate networks and they're working asynchronously. I'll go more into the details of that thing, but it's a good question. Thanks. So yeah, okay. So I'll go more into the formulation of our reinforcement learning problem. So let's talk about the state. So we use a limited number of state features because in the end, we didn't want to have a really high overhead. And so we reduced the implementation of overhead by using like only the most correlated states, because we do some sort of like feature selection. And then also we observe in our work, like the RL agent is more sensitive to the reward rather than the features itself. So in the end, like adding more features doesn't really help. So in the end, we use a 6-dimensional vector of state features where we have, like, for example, the size of request, the type of request, the frequency, and these kind of for each page. And then we quantize the state representation into bins to further reduce the storage overhead, because we were trying to optimize while we were building our RL system. And now we'll talk about the reward, which is like one of the most important aspects of reinforcement learning. And as I mentioned before, reward defines the objective of what you're trying to achieve. So there are like a lot of different ways you can set up the reward. You can think about as optimizing for latency, for throughput, or for energy, or even it could be multi-objective optimization. So in our case, we try to formulate the reward as the function of request latency, because it kind of encapsulate 3 different aspects. For example, the internal state of a device, if there's like a read-write, because there's like asymmetry in the read-write, so you would be able to capture if you just provide this request latency, or if, for example, if there's a garbage collection happening, and it's not really in the background, but it comes into the, when you're trying to serve a request, then you will see it like when in terms of this kind of reward, because it will be a part of the latency. And also, as I mentioned, in the state, we are providing the information about the size of the request. And then if we provide this information on request latency, so indirectly, you're kind of capturing the throughput as well. And also the evictions as well. So indirectly, this kind of formulation is able to capture like a lot of different objectives which you are trying to optimize for. So it's a good reward, but in the end, you can have like a lot of different options to set up your reward, whatever is your objective in the end. So and now I'll talk about the action. Like I mentioned, for us, the goal was to just select like the action was to select like which storage device we should put the requested page. So we made like a really simple action, which was like either fast or slow. And in case you have more devices, then it can be easily extended. So this kind of action allows for easy extensibility to any number of storage devices. So, example, if you have 10 devices, then there will be 10 actions. So we demonstrated with like 2 or 3 actions in this work, but it can be easily extended. That's why we use this kind of action. And also, this action proactively makes Sibyl learn to whether to evict a page or to promote a page. So based on this action, the agent can indirectly learn these aspects as well. That's why we formulate the action in this way. Now I will provide a brief information about like our design and our implementation of Sibyl. So first, let's discuss the execution model of Sibyl. We implement Sibyl in the host OS, where for every storage request, Sibyl uses an RL decision thread to make a data placement decision. And in the background, we have another thread, which is called the RL training thread that works in the background, and it's collecting information about the state, reward, and action. And we keep on training in the background, like I mentioned before. So, and then periodically, we update the weights of the RL training thread to the RL decision thread. So in this way, like this RL decision thread is completely out of your critical path, and everything is happening in the training, and then you keep on updating your weights based on the current information. And this two-threaded implementation runs asynchronously, and that's why we don't really have any interrupts or any issues in terms of like making a data placement decision. Now I will go into the implementation of each thread. So let's first discuss the RL decision threads in the thread where we decide the data placement decision. And also we are collecting the information about our decisions as well. So whenever you have a request, so first we will have an observation vector, which is kind of the state information. And we provide the state information to Sibyl, which acts as the agent. And based on this state information, the inference network will come up with the probability distribution of all the different action. And then the Sibyl policy will decide which action is the best action. And then we will perform that action of the data placement. And also, meanwhile, we are also collecting in our experience buffer, all the information about like what was the state, what was the action, and what was the reward that we got from the hybrid storage system in the end. So this experience buffer is used in the RL training thread for training of our training network, which is running in the background. So what we do is like we have all the experiences which we collect while the execution of Sibyl. And then we keep on storing everything in the buffer. And once the buffer is full, then we start the training of the training network. And this training network learns all the decisions which were made in the past. and also their impact. And so, but to enable this execution of like I mentioned before, that we didn't want our decision making to be in the critical path. That's why we run both of this asynchronously, and periodically we update the weights from the trained network. So they have been updated with the new data placement decision and past experiences, and then we update it with the inference network. And these networks are quite small, so I'll talk about these as well. That's why it's not really a big effort when you were trying to transfer the weights. And we periodically update these, and in the end, your Sibyl is able to take into account all the previous action which are happening. So it learns from its past experiences. So it's not really static; it's dynamic in the end, and it's also able to satisfy the decision-making latencies. So let's talk about the training and the inference network. Like I mentioned, so the input to our training network is just the observation vector, which is the state information, like the size of the request, the type of request, and other features which we have in the 6-dimensional vector. Like I mentioned, we have a really simple network, which is in the first layer, it's a fully collected network where we just have 20 neurons. And in the next layer, we have 30 neurons. And at the end, we have 2 neurons, which represent the action. So if you have more action, there will be more neurons. And in the end, that's it. We have a really small network. And this network produces a probability distribution of all the Q values. So each of the action will have it will produce a probability, and then you select the highest probability, which maximizes the Q value in the end. And based on our experiment, we saw that the simple feed forward network was enough, and we don't really need a super big table to try to to predict the Q values. And also yes.
How would compare the size of this network to the size of that table? Could you give us some?
Yeah, I mean, yeah, you can think about it if you have, for example, 10,000 pages, then you will have 10,000 rows in the table, and easily it will explode. If you have 1 million of these pages, then for each of these action, and if it's a different page all the time, then you could have 1 million of these rows, and it explodes this way. But this case, it's a super small network, which is where I have some numbers on there, is around 100 kilobytes of network, which is quite small. So that's why the computation overhead is quite small as well to calculate quickly the Q values using this small network. So that's why it's quite it's not cost prohibitive in that sense.
Mm-hmm. Thank you.
Sure. And like I mentioned, we use the same network for training and inference. So we just copy the same network, and we do a parallel execution of these, and they run asynchronously. And so they're not really coming into decision-making process, and we can just copy the weights from each other eventually. So any questions? Right. So I'll move into the key results. So we perform real system evaluation for both the dual hybrid and tri-hybrid systems. Over here, we show our evaluation setup that consists of multiple different storage devices. We implement everything in the host OS of this AMD CPU. In our dual hybrid configuration, we evaluate 2 different settings. First is the cost-oriented hybrid storage configuration, where the difference between the latency of the high-end SSD and the low-end SSD is quite large. And then we have a performance-oriented hybrid storage configuration, where the difference between the latencies of the 2 devices is not that huge. And then in our evaluation methodology, we have 18 different workloads from MSR, K-Bridge, and File Benchmark Suite. We compare our Sibyl policy with the 4 state-of-the-art data placement baselines, 2 are heuristic-based, and then we also have machine learning-based policies. So let's look at the results over here for cost-oriented hybrid storage configuration. So on the x-axis, we have different workloads from MSR, Cambridge suite, and on the y-axis, we have the latency. We have different bars for different policies, which we compare, and we also have the slow-only policy, which is if you place everything in the slow device, and then we always compare everything with the oracle. That's the ideal we would like to achieve, but it's not really practical to do it. So in the end, we see Sibyl consistently outperform all the baseline policies for all the workloads, and it's quite good that it's able to adapt for all the different workloads dynamically on the fly. And if we talk about the performance-oriented hybrid storage configuration, where the two devices have similar latency, we have a similar plot for those. And for some of the workloads, we see like the baseline policies are ineffective, even compared to the slow-only policies, because they're performing even worse than that. So in this kind of, because probably these policies were not really tuned for such an configuration. That's why they don't perform really poorly there. However, Sibyl is able to provide 21.6% performance improvement by dynamically adapting its data placement policy for both the workloads and also the device configurations. However, there were two workloads where we see, like, compared to other baseline policies, Sibyl is performing a bit poorly. And we observe these workloads are a bit really write intensive. And have many random requests. So in this kind of policy, maybe we show in the paper that if you do like frequent retraining and if you optimize the hyperparameters, Sibyl can provide good performance improvement here as well. So in the end, Sibyl is able to achieve 80% of the performance of an Oracle policy that has the complete knowledge of the future excess patterns. And we also evaluate mixing of workloads. So for example, rather than having a one specific workload, we mix two or more workloads together. So in this kind of scenario, what will happen is it will test the adaptability of Sibyl even more. And it leads to kind of unpredictable execution where there are requests coming from different workloads at the same time. And so it kind of mimics the distributed workload scenario as well. So over here, we have performance-oriented configuration on the left and the cost-oriented configuration on the right. And we have different mixes over here. And over here, we also have two different settings for Sibyl. One is Sibyl default, where we are using the default hyperparameters for Sibyl. And then we also optimize this further for this kind of setting, when you have like a lot of this mix of workloads. We have optimized hyperparameters for each workload. And then when we compare this policy, we see the Sibyl default provides up to 27% higher performance than the baseline policies. And if we use the Sibyl optimize, it's able to even provide more benefits, which are around 7% higher compared to the Sibyl default. So in the end, like if you optimize your hyperparameters, you can even achieve even more performance. And we also, like I mentioned before, like we tried different features, and in the end, Sibyl is able to come up with like which features it should use. So we have some experiments on that as well. So over here, we have examples on workloads on the x-axis, and the y-axis again is the latency. And each bar over here represents different features which we are using. So for example, if in the first bar, we are just using the reuse distance, and in the next bar, we are using the frequency of a page. So, and then we just provide these features, like one feature or two features to Sibyl, and Sibyl itself comes up with like which is the best feature it should use. And then we have a mix of features. We have, like, instead of using just one single state feature information, we use like a mix of features. And then Sibyl automatically decides, like for certain workload, which feature is more important, whether it's reuse distance or it's the frequency of the page. So it automatically does the job rather than statically setting up these values. And in the end, we use this all features, which were like we actually have like more features than these, but the all features represent the 6 features which we use in our in the final configuration. And once we provide all these 6 features, the agent comes up with the best feature, which is based on the workload characteristics. And like I mentioned before, you can even have like even more features than these. You don't really need to restrict yourself for feature, but in the end, the reward is more important. And I'll come back to that as well when I'll discuss about some important points about RO. So Sibyl automatically decides which features are important to maximize the performance of a running workload based on the workload characteristics and also on the device characteristics. And in the end, we also wanted to evaluate the extensibility of Sibyl to provide like how it will perform if we have more devices. So if you want to, like I mentioned, if you have like a heuristic policy, then you will have to manually code all the different scenarios if you extend your device, if you have 3 devices or 4 devices. But in Sibyl, what you have to do is you have to just add a new action. So instead of 2 actions like fast or slow, you will have another action, which is like the mid device or like slower device. And then we also added like the remaining capacity of the new device in our state information. So the agent is aware of like how much capacity is left. And that's it. And Sibyl itself comes up with the new policy. You don't really have to do anything. everything happens automatically on the fly. So over here, we have the results for all the MSR Cambridge workloads. On the x-axis and the y-axis, the request latency. We have the heuristic policy, which is state-of-the-art policy. It's actually an extension of the CDE policy, which I showed before. And actually, to implement this policy, we had to spend quite a bit of effort to handle all the different scenarios, like I mentioned about the migration, the promotion. And however, when we had to do Sibyl, we just added these two things, and Sibyl was itself able to come up with the best policy. And in the end, it was able to outperform the state-of-the-art data placement policy for tri-hybrid system by 48.2% on a real system. And so in the end, Sibyl reduces the system architect's burden by providing ease of extensibility. And all of these performance benefits.
Gagan, I have a question here.
Yeah.
Can you hear me?
Yeah, I can hear you.
Okay. Good. So this is certainly this tri-hybrid system extension is very interesting, right? Because it enables you to extend the policy easily.
Right.
Actually, I have two questions over here. One is, you say that you add only two things, new action and the remaining capacity.
Right.
How come only two things? How come nothing else?
No, yeah, I mean,
is this really enough? Or so I can imagine adding many other things potentially, right? Like, why don't you do that? Why are these two things enough?
That's a good question. So we can add actually like a lot of things if you want. Like I was mentioning about it before as well. In the state information, you can add like more information about the characteristics of the new device or like other features you can think about. But in the end, like what we saw in our experiments, the reward is the most important thing. So adding more features doesn't really help. Mm-hmm. So you can keep on adding like as many features as you want. But like in our experiment, we see that it doesn't really help. So I'm not saying it's an extensive list of features which we add. Of course, you can add many things. But like the way what we want to demonstrate it's just like the action space and the feature, and you add these two things, and the things are able to work for you. But of course, you can
so basically, it's an empirical observation, right? So the reward function that you have is also working for a tri-hybrid system.
Right.
Okay, that makes sense, I think. Okay, the second question is, you showed us the Oracle results for the dual hybrid system. Do you have any Oracle results for the tri-hybrid system? Because that would enable us to really check if this, let's say, if Sibyl is actually, how Sibyl is close to the best possible performance.
Right. Yeah, actually, we spent like quite a bit of time and effort on coming up with the Oracle for this tri-hybrid system. But in the end, we realized it's not that easy, because even for dual hybrid, actually, it's not that easy. Like, what should be the Oracle? What should it look at? Like, should it just look at all the different characteristics? How should it decide like how much of a window further should the Oracle look? And depending on the workload, that computation could be quite huge as well. And in the end, like for tri-hybrid, it was even worse. Like we couldn't really, and there's like no, I think like in literature as well, there's not a gold standard of like how it should be, the Oracle should set up. And for tri-hybrid, we couldn't come up with any good Oracle. And I think it would be nice to have, but it's kind of like a bit debatable, like how it should be done and what would be the best Oracle.
Mm-hmm. Yeah, I mean, I agree. In general, it's very hard to figure out an Oracle that is the best dynamically, right? It's
right.
Even with two devices, but once you go into 3 or 4, it becomes much harder.
Right, exactly.
Yeah. But do you have any intuition as to how far you could be worse than the best possible policy, given that you don't know how to implement that best possible policy?
I don't want to say any. I don't want to make any claims. I won't say anything.
Yeah, I think that's good to somehow figure out, right?
Like one point of reference could be that you place everything in the fast device.
Exactly. Yeah, that's basically that's a good, let's say, very large upper bound.
Right. So that would be like quite a bit of upper bound, depending on like what's the latency difference between the high end and the low end. So if you're placing everything in the high end, and I don't know, your policy somehow is placing everything in low end, you're like quite below the high end, the bound. But yeah, I think it could be a good starting point just to put everything in the fast and compare with that, like how worse you are.
Mm-hmm. Yeah, I think that's it's good to strive for that upper bound, right?
Right.
Yeah, it'd be good to see those results.
Right.
Okay, that's all I have for now.
Yeah.
Thanks.
Based on an obvious question, but if you can put everything to high-end SSD, why wouldn't you do that?
Yeah. No, that's a yeah, exactly. So I mean, that's like a hypothetical scenario, because usually the problem we have with hybrid system is you have a fast device which you don't have enough capacity there, so you can't really put everything in the fast device.
Like Oracle.
Exactly. I mean, you can suppose that they like somehow you have a workload which can fit there, and you take like, I don't know, you don't really consider like the complete workload, but you just focus on like how much you can fit there. So you can somehow make some sort of scenario, but that's the problem, right? Like fast is expensive, so you can't really afford it, and that's why you want. So in the ideal world, you want the performance of the fast and the capacity of the slow. So that's what you like want to achieve in the end. So yeah.
Yeah, but that's exactly why you want to do ideal studies like this, right? You want to see how far away you're from the ideal in the end.
Right.
I mean, that's what we do in processor caches also, right? How far are you away from an ideal L1 cache, ideal L2 cache,
right,
ideal L3 cache, or ideal memory,
right,
ideal branch prediction, and you want to close the gap as much as possible in the end.
right.
Given that you have the limited capacity in high-end SSD, still like there's an optimal algorithm that obeys the constraints, and shouldn't it be the Oracle that obeys the constraints?
Yeah.
This part doesn't seem like little.
Yeah, so that's the thing. Like, so the Oracle, like that's what we were trying to do. Like, we wanted to come up with the Oracle, which takes into account the capacity aspect as well somehow. So once the capacity is full, then it moves the data. But in this case, we were kind of like, okay, so if the dual hybrid, then you can do that. But it's tri-hybrid. Okay, so should we move data to the mid one or to the slower one? So they're like even more another layer of decision. Okay, if the mid one is full as well, now we move from the fast one to the slower one, or should we move everything into the slower one? So there are like a lot of decisions there. So it's quite tricky, the Oracle, which takes into account the capacity constraints.
Yeah, that's why you said maybe we can just ignore the capacity.
Yeah, exactly. So that's not the real setting. So. Cool. I'll move further. Okay, so as I mentioned, this Sybyl's overhead, these performance overhead come at a modest cost. First, in terms of the storage, which is 124 kilobytes, which we need to implement for the experience buffer, for the inference and the training network. And as I mentioned, these networks are quite small, so you don't really have a super big overhead for those. And then we have per page, we have a metadata to store this the state information, which is 40-bit in the end. So it's not that huge, because in the end you need for all sorts of hybrid storage policies, this metadata. The inference latency, which we have, is of 10 nanosecond, which is orders of magnitude smaller than even a high-end SSD, which is in microseconds. So it's not, the inference latency is not really a problem. The training latency is 2 microseconds, and as I mentioned, these training and inference are happening asynchronously, and we just transfer the weights. So it's not really a problem if the training takes more time as well, because we just copy the weights. So in the end, there's a small area overhead, small inference overhead, and then we are able to satisfy the prediction latency of a data placement decision as well. So that's why all of these Sibyl is quite practical in that way. And we tried everything on the real system, so we show it works as well. So also I would like to talk about the explainability analysis. So until now, I talked about, okay, everything is working. We did a lot of effort, and we came up with like how to implement things, how to devise it, like how to make it as a data placement problem as an RL system. We demonstrate everything works, but still, like there's a big gap between like understanding how these RL is taking decisions. So that's why we wanted to provide some sort of intuition into how this RL is coming up with different actions. So we perform an explainability analysis where what we do for each of our workload and all the devices in a dual hybrid system, we extract the actions of Sibyl. So, and on the x-axis, we have, again, the workloads, and on the y-axis, we show like the preference for fast storage. So how many times the agent is like, the agent prefers the faster storage over the slower storage. And then we wanted to like correlate these based on like our understanding of the workloads and understanding of the devices itself. So over here, if we see like the pointer is not there, but anyway, like if you see for performance-oriented configuration, we have this PROC2, and then we have this PRM1 workloads where the preference to put anything in the fast storage is quite low. And when we look at the pages in this, on average, the workload characteristics, these pages are quite cold in the sense you're not really accessing them a lot. And also a lot of pages are sequential. So if you store these pages in the memory, they are sequentially accessed, so you will have to get rid of them eventually. So there will be a lot of evictions. And we saw that that Sibyl was able to learn this. And then we have these workloads, like for example, there's proc0, then there's proxy0. This one, there's a high preference to put everything in the faster storage. And if we analyze the workload characteristics of these workloads, we see there are like a lot of hot pages in this. So there are like a lot of pages which are frequently accessed. So Sibyl is able to learn this thing that it makes sense to put this workload in the faster storage because we are going to access it again and again. But if we compare like between two different devices, like the performance-oriented bar and also the cost-oriented. So in the cost-oriented, mostly Sibyl is always trying to put everything in the faster storage compared to the slower storage, because our intuition is that there's a really high gap between the latencies of the faster and the slower device, and Sibyl is able to learn that if we put everything in the faster storage and if we serve it there, it would be still better, even then if we get the eviction penalty, which will be in the background still. So it's able to dynamically adapt, but in the case of a performance-oriented system, where the latency difference is not that huge, Sibyl performs more dynamic decisions. So we provide kind of intuition into like how, based on the workload characteristics and based on the device characteristic, how Sibyl is able to learn the decisions and how these how they make sense in the end. So in the end, Sibyl performs dynamic data placement decisions. And we provide many more experiments in the paper in terms of throughput evaluation, in terms of unseen workloads, which we don't really optimize the hyperparameters. Then we also evaluate different hyperparameter values and we show the effect of all the important hyperparameters. And then we also provide the sensitivity to fast storage capacity. So if you change the size of the fast storage, how does it affect your data placement decisions? So we have many more results in the paper, so I would recommend you to go and read our paper. And we open sourced our code on our GitHub repository, so everything is implemented in the software side, so you can easily go and check it out, and it's already being used. And so I would recommend you to use it, and if you have any issues, please write to us.
Yeah, I have a question with respect to the extended results. Do you have any statistics about how much of the fast storage is in use over time, over the execution of a workload? What percentage of the total storage?
No, we don't have those. Like we didn't calculate this.
I mean, I'm asking this because I don't know if you are going to be using all the fast storage all the time, but probably not. If we look at the results you show for explainability,
right?
But this could also, those statistics could also give us some information about, or some hints about how much fast storage you really need, right?
Right.
You have a system with three different storage devices. Maybe it can give you also an idea of how much you need, and in that sense, how much you have to spend on your hybrid storage system.
Yeah, that's true. So it kind of indirectly, we can say that from our fast storage capacity analysis, you can kind of understand like once we change the capacity and how the performance is changing. So eventually the performance kind of saturates. So which kind of indicates that you don't really need more capacity, right? So this actually, it's a good point that you can kind of infer these things as well based on like how your data placement policies behaving or how is the performance in the end. So it's not always good to have like as much capacity you want, right? So that's a really good point. Yes.
Also, maybe you should you haven't like extended the results for this extensibility analysis in like 3 storage.
Yeah, right. So no, we didn't really do that like for 3 storage. But like I assume it would be good to do that, but we didn't really perform those like for a 3 storage system. And also it's like it's one of the way of like we came up with like to show the explainability, but there could be different ways as well. So our explainability was like to compare with based on the workload, because that's how we were envisioning everything, like change in workload characteristic. But there could be other ways as well, like the way you can explore explainability. So it's just one example.
I have another question about the hyperparameters. How costly to update the hyperparameters? We have seen some slide with one plot that the default hyperparameters are quite good and actually they outperform other policies. But you can always do better, right?
Right. So actually, this is like one of the things I'll come to when I'll in my discussion slide. There's like this hyperparameter, like people don't really talk about it, but it's really a big problem as well, because it like your performance really depends on the hyperparameters in the end. If you make the best model, you make the best setup, and if you don't really set the right hyperparameter, you will get really bad performance. So in the end, it's quite a pain like itself, like to somehow set up the right hyperparameter, and you always spend a lot of time setting those up, especially in these Rahul systems as well. Like you really don't really know what's going wrong. Like it's just the hyperparameters, or maybe it's the structure of a neural network, or it could be your reward, or it could be like the state information. So there are like even more aspects which you have to take into account when you are designing like an Rahul system. So it's quite complex. So it's a big problem. Like, I mean, we should kind of talk about it and address more. So I'll come on that as during the discussion point as well.
Okay, thank you.
So are you going to also talk about unseen workloads, Gagan?
No, I wouldn't talk about those.
Can you give us an idea of what the results look like there and how you did the study? Because that's important in the end, right? It's good to train a mechanism on some test workloads and some training workloads, and then test the mechanism on complete different workloads.
Right. So in this RL, it's not really like a training phase or like a testing phase as such. But when we talk about, like when I say unseen workload, it means in a way that we didn't really optimize the hyperparameters for these kind of workloads. So the way we did all the studies is we take like these bunch of workloads, which I showed. We randomly select like half of the workload, and we do like hyperparameter tuning. We spend some time on like finding the best hyperparameters, and then we just use those hyperparameters throughout our studies. In the experiments where we were showing the comparison, where we had the Sibyl default parameters and Sibyl optimized parameters, there we optimize for each workload the hyperparameters. And we showed if you optimize for each workload, you can gain around like 7% more performance on top of what you were already getting by setting these default workloads. So for these unseen workloads, we don't really change any hyperparameters. We just they're completely different, and they have never been seen. The hyperparameters are the ones which are default. You still get really good performance there. We show with the default hyperparameters, but in the end, like I mentioned, if you optimize them further, probably you will get even more gains.
So do you have a slide? Because I'd like to discuss this a little bit more if you have the results.
Yeah, actually, I don't have it in this slide deck.
Okay.
Yeah,
but I think in general it makes sense to not optimize the hyperparameters to the workload, because many people don't have that sort of luxury in life.
Right.
And in system design, right? So it's I think the realistic results are really those where the hyperparameters are obtained. That's what I call training in reinforcement learning, right? Hyperparameters are optimized for some set of workloads,
Right.
And then in real life, a complete different set of workloads run, and you're stuck with those hyperparameters that somebody optimized for you.
True. Yeah, that's what actually we try to do as well. Even with all our experiments, we tune for a set of workloads, the hyperparameters, because you need to tune those. Otherwise, if you're lucky, you will get the best hyperparameter in a brute force manner in the first try. But you always have to optimize. That's what we did. Like we take like a bunch of workloads, we optimize the hyperparameters, and then we use those ones throughout. But in the end, like you said, people can be stuck with the same hyperparameter. Then if someone didn't really optimize, then it wouldn't be the optimum system.
Yeah, I mean, that makes sense, I think. So is there any potential for future exploration where you can potentially optimize the hyperparameters online? This requires, of course, a much smarter machine learning algorithm.
Right. So actually, there are some efforts to find the optimum hyperparameters, like maybe even applying some sort of neural architecture search, because you can have like a lot of options for hyperparameters. There could be like hundreds of hyperparameters depending on like how you consider your system. So there have been like some works which try to come up with the optimum parameters using neural architecture search, but I don't know if you can do it on the fly, those things. I didn't really explore that part.
Yeah, I know you didn't explore, but I think this is something that can, and a lot of this is probably algorithmic research in machine learning and reinforcement learning to understand how you can dynamically optimize this difficult thing that really should be optimized if you really want to get the best out of learning.
Yeah, for sure. I'm not sure if there are like some works which do it on the fly. Maybe could be, but yeah, it's an interesting direction, I think, itself. So we have open source our code on a GitHub repository. So you are free to try, and if you have any issues, just let us know. And people are already using it. And like I mentioned, I would like to discuss like some of the things which people have already throughout this seminar, people have already pointed out. For example, the first thing is need for explainability. So we tried to give like some sort of intuition using our analysis and trying to correlate these action with the workload characteristics. But RL or ML in general is kind of like largely a black box. So especially in our community as computer architects, people just apply RL algorithms or machine learning algorithm, but they don't really provide intuition into why they are doing what they are doing. Because as a human, you would like to understand as well, like how it's behaving, so that you get some sort of like confidence in your machine learning algorithm that it's going to work always. So like we did some effort in that way. We tried to do it, but of course there's like room for improvement. You can do a lot of different ways of explainability. So I think it's like one interesting direction in general. There's a lot of research going on. It's a research field itself. People are trying to come up with different ways of providing explainability, but we should take some of the lessons from that field, maybe apply in our field as well to provide like better explainable algorithms. So that's, I think, one of the important things which through our work we wanted to convey. Then another thing is the importance of reward. So like I mentioned like a couple of times, like reward is quite important. And even like recently I've seen like some works as well where they're claiming like reward is all you need. You don't really need anything else. So even if you don't have if you just have one state feature and still the agent is able to work if you have the right reward. And this setting up the reward is quite like a human driven effort. It's not really, you can like an algorithm can come up with that. You need some designer expertise, like you need to understand like how the system behaves. So I don't think like the human is going to be replaced. The human will be in the loop for this, at least to set up the initial reward and coming up with like these state features and these things. But the reward is like super critical. So I think we spend like most of our time while like trying to formulate the problem on the reward itself. So this is one important thing which is critical in terms of like future works as well. If people are trying to do something on our side, to think more like what's the optimum reward in terms of just trying to add more features.
But here, do you have any intuition about how to select a reward, something that can somehow, or is it just brute force?
Not really brute force. It's more like I mentioned, like it's kind of like it should convey the objective in the end, what you're trying to achieve, right? So from the reward point of view. So for our objective we wanted to reduce the latency. And then once we were doing experiment on the real system, we kind of saw that the latency varies a lot depending on, it's not always like if you're using a simulator, then you have a fixed latency, which is always depending on the your workload or like what a request is coming in. Those are like few scenarios which can be easily learned. But if you do it on a real system, the latency varies a lot. And then we kind of like had to spend time thinking about like also if the latency is varying a lot, like how should we craft the reward itself? And we tried a bit of different ways of crafting reward. Then we had to, like, I talk more about this in paper as well. We gave like a small penalty as well when there's like a lot of evictions happening. So we also track the evictions and the reward. So in that way, like you don't really do a brute force. You have to like first you should be clear about what the objective is. So if you're optimizing for that objective, so that's straight away you just provide that as the reward. And then you have to see like empirically or once you run the experiment and like how your agent behaves to like the settings. And then again, like hyperparameters also play a role here. So you have to also see the importance of like how this mix of reward and hyperparameter interact with each other. So there's a lot of empirical study you do there as well. So you need like some sort of design expertise there, setting up things. You can't just brute forcefully just set anything there. And the third most important point is like which we have been talking about until now. It's like the hyperparameter tuning. It's super critical. It's really, we spend a lot of time on that, and it's really critical for the performance. And especially like now we have another component like the reward itself. You spend so much time, you don't know what's happening. And then on top of that, you have hyperparameters. So if you just start from the beginning if you're trying to implement or come up with a new idea on the RL side, you will get lost because there are so many things that are happening. Then we as like architects and which are trying to work on like machine learning side, there's like so many hyperparameters, and it's really like one of the problems no one really talks about in our field, but it's really a problem. And you just like usually if you read papers and they talk about like these are the best hyperparameters. We did hyperparameter tuning, but no one discusses like how painful it is, like how you have to spend so much time to come up with the right hyperparameters and how they affect like when you go in a dynamic scenario. We have been discussing about these things during the seminar, but it's really one of the critical things. So in my opinion, like these are like if I have to give my 2 cents, so this would be like 3 things which you should going forward keep in your mind when you're doing like any sort of research in like machine learning field in RL in general. So it's really important. So, I mean, there are like way more things you should consider, but these are like the most important, which I can like recommend, and no one talks about it. So before I conclude, does anyone has any questions or any comments? Very cool. So I'll conclude my talk. So we introduced Sibyl, which is the first reinforcement learning-based data placement in hybrid storage systems that provides easy adaptivity, extensibility, and ease of design and implementation as well. We extensively evaluated Sibyl on real systems using many different workloads, and we show that Sibyl improves the performance by 21.6% on a dual hybrid system, and on a tri-hybrid system, Sibyl provides 48.2%. And Sibyl is able to achieve 80% of the performance of an Oracle policy, which is storage overhead of only 124.4 kilobytes. And we have open source our code on our GitHub repository. Please do try, and we'll be happy to have any feedback or any questions you have. So thank you. Thank you for your time.
Thank you very much. I probably want to ask you a couple more questions.
Sure.
So the first one is with respect to what could be changing in the actual architecture to make these techniques even more applicable or even more efficient, right? So designing this kind of agent requires you to have access to information from the system, right? Because
Right.
this is data-aware action.
Right.
And could you comment on maybe if you have missed any metrics that you think could have been very useful for the agent to make smarter and faster decisions, for example?
Right. So I think there are like two aspects to the question. One is like what are the informations required and how we can provide those. And the other are like if there's some information we are missing. So if we try to like focus on the first one in terms of providing the information. So like I mentioned, we had this 40-bit metadata overhead that we were trying to provide information in terms of the request, in terms of the access frequency of the page, the size of the page, and these kind of information like reuse distance and these things, which it's a separate problem itself because and it's not really related to our mechanism. It's like when you have a hybrid storage system, you need to keep track of where the page is placed. Like whether it's in the fast storage or the slow storage, you need to keep track of those things. And then again, you also provide some sort of information. In our case, we took these 6 features, which I mentioned. So there's an overhead of like managing this metadata. And it could be quite huge as well, depending on like your scenario. Like it could be like where to store the metadata. Like that's a separate problem itself, which if we have to going in future, if we really want to use like hybrid systems or like some sort of intelligence in like, even if you go for heuristics or like machine learning, then you need to figure out a way to manage this metadata. And they have been like, we were discussing about like certain like different mechanism, how we can optimize the metadata. And like, for example, you need to know whether it should be in the DRAM because you need fast access to the metadata as well, because if you're doing some excessive. So that's a separate problem itself, which should be solved as well. But it's not really related to RL or it's a problem because of hybrid storage system. And for RL side, it's these mechanisms, like there's like an engineering effort which is needed, which in the end it's needed for other things as well, but you need to connect. There's a disconnect right now. If we see like there's a lot of mechanisms which are being done on a higher level language, a lot of libraries which are being developed like mostly in Python. But in the end, like if we wanted to implement these things, like for example, we did it in the kernel space and we had to like somehow connect these libraries, or you have to implement everything in like the kernel space itself. So there's a lot of engineering effort which goes into these things. And when being a researcher, you have to spend those effort as well. So there's a disconnect in terms of like, because most of the machine learning things are being developed either on MATLAB or you can think about Python. So that's a bit of disconnect, which we had to figure out as well, a way to connect it. Because if you have, for example, if your environment is using C, like a lower level language somehow, and your agent is on a higher level language, you have to provide some sort of feedback to it, which could add additional delay, a layer of delay as well. So that's a couple of problems which we saw in like our case when we were doing it. And then like another thing which I didn't really mention is like a lot of these machine learning works, they're done using some sort of simulation or simulator. And I think I kind of refer to it when you go on an actual system, the environment becomes quite different. Like it's the latencies, like I'm just giving example of latency because that's what we saw. And also like in hybrid storage system, you also have like the aging effect comes into play. For example, when we were working on these storage, we started seeing that there was like we were doing a lot of experiments, and eventually the latencies became higher for our like same experiment when we were repeating on the storage. And then we had to like we kind of realized like we have been running it quite a lot, like these devices, and we have been running a lot of like read-write operations, so the latencies were a bit higher, and these kind of scenario which happen on real system, which you don't really see on when you're just using a simulator. So this would be one thing as well, like I would recommend like people to do like more real system if you can. Of course you can't always use a real system in all the scenarios, but for some cases you can. And in terms of like if there was some other information which we missed, I think it could be like there are like a lot of features like we have been discussing as well. Like there could be other state information which you could have provided, like so many features in terms of bandwidth. You could provide some information of a bandwidth consumed, or what's how much you have in the queue of your SSD, how much page information is there already. So there's a lot of different things you could have provided. But like I mentioned like repeatedly about this thing, that in the end, like what we observed, even we tried to provide more features, but it was not really helping, because for us, like the reward was the most critical thing. So yeah, it could be like, it would be nice to try with even more features and maybe different optimization objectives as well. Like right now we are just optimizing for latency. Maybe in future it could be like try to do like a multi-objective, like both latency and energy consumption, like these things as well. So there's like a lot of things which could be done.
Yeah, but there could also be very useful to have sort of doing accurate simulation, right? You can say the simulator, you have way more control, so you can basically get all any metrics and statistics you want.
Right.
In principle, right?
Yeah, that's true. But I would point another thing as well. Like for us, like we actually started doing with the simulator, and the hyperparameters which we were using on simulator didn't really work on the real system. We had to again do the complete hyperparameter tuning, because like Onur also mentioned before, that in a real system, it would be that you have to retune your hyperparameter, and the same thing happened with us. What we were using on the simulator didn't really work. It was so these things as well, like which you really see it like once you start doing an actual system, these things.
Yeah, I was also thinking about that in reality there is some a starting cost or cost at the beginning in training the agent and tuning hyperparameters and so on, right? That is costly and can affect the performance in production, while having some accurate simulator that could faithfully represent what's going to happen in the real system would be really nice.
Yeah, that's true.
Yeah, I can understand the limitations.
Yeah, I think both the options like has their pros and cons. I mean, ideal would be like if you have both access to both and you try on both, but I guess it's quite a bit of overhead to do both.
Okay. Are there any other questions? I don't see any questions in YouTube or in Zoom. They may ask you something else, general thing, right? Because here we see that these RL-based agent is performing pretty well in hybrid storage systems. We know about other works that are doing similar approach in hybrid memory systems, for example, like the Clayo paper that you compared to in the beginning. So it seems like RL agents are promising in order to help the microarchitecture to perform better.
Right.
And hopefully we will see them in real systems more and more in the near future, right? And my question is, so actually two questions. The first one is, what would you identify as the right places to start placing these RL engines, RL agents? I guess that the hybrid storage system is one of them, you're going to say.
Right.
And the second one is, do you foresee a future where these RL agents can somehow interact and cooperate in some way, because in the end, all different components of the microarchitecture are connected, right?
Right.
So what do you think about this?
Yeah, that's a really good question. So if I think about like other like places where you can place RL agent, this is like one, I think like the first question which comes to mind if anyone wants to do like any sort of research on applied reinforcement learning for microarchitecture. So like except for hybrid storage, the direct place to apply would be hybrid main memory, which we also discuss in our paper about it, and it will have its own set of challenges, because in our case, for example, in hybrid storage, the storage is a bit away from the main processor, right? So you still have some latency which you can afford for decision making. So it was a bit like still easier for us to have some sort of latency gap in terms of if the agent takes some more decision making time or something. But if you go to main memory, it would be like you wouldn't have the same like same latency as well. So you would have to somehow come up with like more intelligent mechanisms. So maybe the issues in terms of this metadata overhead would be more prominent as well there. So in our case, it was a bit easier. So each level has its own challenges. From our group, there have been some works on like applying reinforcement learning for prefetching or for memory controller. So basically you can apply it anywhere where there's some decision making happening in the system. So wherever you can think about like some decision to be made, like you can apply RL, because in the end it's just trying to come up with like what's the best action. So it could be in compilers, it has been applied like for coming up with like what's the right optimization. And then even for like actually for a hyperparameter tuning as well, there have been like approaches which are applying like reinforcement learning to find the right hyperparameters as well. So there's a lot of different places where you can apply RL, like just think about the way where there's a decision making, like RL can help there. And there was a second question, I forgot.
Yeah, so the last part of the question was if you can see somehow these different agents coordinating and helping each other.
Right. So for sure, I mean, like now there's already a lot of efforts to put like some sort of machine learning algorithm, like Perceptron are already there. And then like in the processor, so there would be some intelligent agents. And it's a really good point that like a lot of work is done at the moment, isolation from the other agents. So we don't really like this part, we made this part data placement intelligent, but the rest of the part is still not intelligent. I wouldn't say dumb, but it's not intelligent. So we don't really take into account the interactions, how it would affect, and actually we were also discussing about like some sort of interaction having a dual agent which does for example data placement, the other one is doing migration in the background, and they both are kind of doing some sort of handshaking with each other, and their actions are going to affect each other's actions. So that would be kind of interesting as well to explore. And I don't think there are like many works which are trying to do that in the literature, and we are just doing everything in isolation. Of course, it's like making one agent itself is quite a bit of work, and like we know from experience, so having two agents would be even more effort. But in the future, it's kind of needed. Like we should study these kind of even in terms of like caching and prefetching, these kind of where I can just right away we can see like there would be two agents which are like the decisions made by one agents are going to affect the other agent. So it would be super interesting to study in future.
Maybe for cache replacement policies and prefetchers.
Yeah.
Okay, that sounds very good. Thank you very much for your answers.
So thank you for the questions.
Okay, so yeah, I don't see any other questions. If there are no other questions from the audience here in the room or in Zoom, then I guess we are done for today.
Thank you. Thank you, Juan.
Thank you very much, Karen, for the great talk.
Thanks.
I hate servers. Nothing is very. It doesn't want to tell me why it's not very.
Oh, you don't know, it's all online, and then it's